So, hello everyone. We are very happy to have Diana Powell here today. She is a NASA Hubble Fellow, more specifically a Sagan Fellow at Harvard CFA. And she will be starting, in fact, as an assistant professor in the Department of Astrophysics at University of Chicago very soon in 2023. Very briefly, she obtained her bachelor's in Astro from Harvard, then moved to UC Santa Cruz for her PhD, which she recently finished. And then in general, she has worked on the nature of extrasolar planets and how they form and evolve, and also on protoplanetary disks and planet formation and atmospheres of the planets in general. So, and today she'll be talking to us about her about her research from results from some recent and past work. And so that's it, I think. Yeah, please take it away.
Awesome. Thank you so much. And it's so cool to be here in person. So it's my first in-person talk in 2 years. But thank you so much for having me. So I'm Diana Powell, and I'm a new Sagan Fellow at the Harvard Center for Astrophysics, Harvard Smithsonian Center for Astrophysics. And today I'm really excited to talk with you all about microphysical insights into protoplanetary disks and exoplanet atmospheres. And so for the purposes of this talk, microphysics refers to the evolution of small particles in the presence of gas. And I hope to demonstrate to you by the end of this talk that we're closer than ever before to connecting the process of planet formation to planetary characterization, in part due to this ongoing microphysical revolution. And so the key question behind all of this research is, what is the origin, evolution, and nature of planets? And to answer this question, I characterize the planetary material and protoplanetary disks, as well as exoplanet atmospheres. And in particular, I use theoretical microphysical tools to uncover fundamental properties of both disks and atmospheres. Okay. So the general picture of planet formation that has emerged looks more or less like this. So planets form in protoplanetary disks, either from the accretion of solids and gas or the gravitational collapse of material. So these disks really represent the building blocks of planetary systems. Then, once the bulk of the protoplanetary disk dissipates, a young planetary system remains. And so if there are gas giants present, they're initially relatively hot. And in diagrams like this, often the second phase is missing, but I include it here because it really represents a distinct observational stage with unique observing signatures and strategies. And then as time progresses, the system will also evolve. Planets will find relatively stable orbits and their atmospheres will also evolve. Okay, so this is the general picture. But what I want to know is, how can we relate these disparate evolutionary stages? And to do this, to really learn about the full complement of planetary systems, so how they form and how they evolve. And we're all really lucky to be alive at a time where we can observe each of these stages in unprecedented detail. So we can look at protoplanetary disks, like the disks shown in high resolution here. As a bonus, we can also see protoplanetary disks undergoing active planet formation, like the PDS-70 system here, where you can see 2 points indicated by the arrows that are thought to be giant planets undergoing accretion. We can also observe young planetary systems directly, like the Beta Pig system shown here. And finally, we now have constraints from over 4,000 evolved exoplanets, as well as detailed constraints from solar system planetary science and cosmochemistry. And so with all of these data, this is really the era to start connecting planet formation to planetary characterization. And the way that I approach understanding planet formation and evolution is from the perspective of chemical compositions using microphysics. So in particular, my research focuses on using these theoretical microphysical tools to uncover the composition of both disks and atmospheres and relate them to each other. And so I'll get back to talking about microphysics a bit in more detail. But first, let's talk about making this connection between planets and disks. And so while this ongoing observational revolution in both disks and atmospheres represents a really exciting opportunity to connect these two objects, that also represents a really significant challenge. And that's because both disks and atmospheres undergo significant evolution with time, such that it's difficult to compare these objects in a one-to-one fashion. Okay, so to understand some of these difficulties and why the microphysical approach is crucially important, let's dive in a little bit deeper. Okay, so what are we actually looking at when we look at protoplanetary disks? So observations of protoplanetary disks are primarily observations of small dust grains or different trace gas species. So these recent observations are spectacularly angularly resolved. So here I'm showing the D-sharp ALMA survey of a diverse, bright group of protoplanetary disks at 1.3 millimeters, where you can see distinct morphological shapes, all the way from large-scale spiral arms to smooth axisymmetric systems. But despite this level of detail, observations are often lacking constraints on some of the fundamental disk properties, such as the total amount of mass in the system, as well as some of the detailed but really important compositional constraints on both the solids and the gas in these systems. And all of this is really particularly true if we look towards the planet-forming regions of the disks. So to get more of an idea why determining the chemical compositions of disks is difficult, let's take a quick look at this vertical cross-section. So here the system's host star is on the right, and it flares out at longer radii as we move to your left. And so planets form in the disk midplane, which makes this a region of particular interest. However, in the midplane, the ice particles that are present in the outer disk are radially drifting inwards towards their host star, which alters the composition of the disk. These grains can eventually reach a hot region of the disk where they lose their volatile material back into the gas phase, again altering the composition. Gas is also being mixed radially and vertically, which changes the composition with time. And to top this all off, there's often gas present in the upper regions of disks, which is often optically thick, such that the regions where we're observing emission are not from the midplane directly. So you really have to care about these effects if you're looking at observations in the upper layers and trying to tie that to where the planets are forming in the midplane. Yes.
Is it okay to ask the question?
Sounds great.
Why are the icy solids moving inside?
Yeah, so we'll talk about that a lot, and I think the second version of the talk, but they're drifting. They basically feel gas drag because the gas feels this outward pressure gradient from a vacuum on one side. So the gas is rotating slightly subcaplarian, but the particles, well, depending on their size, are more or less better coupled to the gas, but they're feeling the drag. Remove some of their angular momentum and spiral inwards. So what about planets? So what are we actually looking at when we look at young and evolved planetary systems? So a primary source of compositional information about planets comes from their atmospheres. An example of the data for these objects is shown here for young planets on the left and evolved planets on the right. So here on the left, we're looking at emission spectra of, I think it's 12 planetary mass objects, and on the right, it's transmission spectra of 10 hot Jupiters. And despite the detail that we can observe in these atmospheres, these observations are often hindered by opaque sources such as clouds and hazes, which obscure compositional information and other planetary properties. And so what we're probably looking at are atmospheres that look something like these atmospheric slices shown here. So these atmospheres are covered by clouds. And clouds can either be high altitude, or can be high altitude, or they can be low altitude. If they're low altitude, you might be observing some unobstructed regions of phase space above the clouds. While if they're high altitude, you can completely obscure all planetary signatures, so composition, and other properties that you might attempt to tease out from spectra. But even if the clouds are low altitude, they can still obscure planetary properties and alter observed gas phase abundances. Also, when we're talking about making the connection between disks and atmospheres, it's worth pointing out that we can often get our best constraints on disks and different orbital regimes, and we can observe planets well indirectly.
So would clouds be also still interesting by themselves?
Clouds are super interesting by themselves. So
Like even the composition of the clouds, right? I mean, probably they're not completely different than everything around them.
yeah, the cloud composition is super interesting. It certainly depends on background planetary properties and the composition of your atmosphere. And as I'll talk about a little bit later, they're also a first order determinant in the radiative transfer in your atmosphere. So they're the primary source of opacity in your atmosphere. Not, well, so they're all that you can see, they determine the planetary climate, and they also shape everything from dynamics to chemistry to transport. So everything about an atmosphere is really shaped by clouds. On Earth, they're the biggest source of uncertainty in models of climate change. Okay. So in both cases, many of the complications with determining chemical compositions boils down to a need for better understanding of microphysical processes. And so in this context, this microphysics refers to the evolution of small particles in the presence of gas. And in the case of atmospheres, microphysics primarily determines clouds and hazes, and in disks, we're talking about dust and ice particles. So by the end of the talk, I hope to have shown you that each of these processes is crucially important in understanding these objects. Okay. So to make the connection between disks and atmospheres, we need better models, better physically motivated models, to interpret current and upcoming observations. And I'll argue that microphysics will be important in making this connection, and maybe it will be key to understanding the origin, evolution, and nature of planets. Okay. So I'll start by talking about some of the initial work that I've taken towards this goal of tying planet formation to characterization. So I'll start by talking about planetary atmospheres with an emphasis on clouds. And then I'll move on to talking about protoplanetary disks and their fundamental properties, such as their total mass. And then I'll end the talk, hopefully with enough time, to bring these two topics together to discuss the evolution of carbon monoxide and carbon monoxide gas and disks. Okay. So let's talk about clouds. Okay. So we all have some intuition about clouds from our familiarity with clouds on Earth. But clouds are crucially important beyond Earth and are in fact the dominant opacity source in most planetary atmospheres. So clouds are important tracers of atmospheric physics, such as mixing and transport. Clouds regulate the planetary climate through regulating radio transfer and chemistry. And clouds must be understood when determining precise atmospheric abundances. Also, often the clouds in an atmosphere are really the only thing that we can see. So it's therefore an absolute necessity that we understand clouds when we're interpreting planetary atmospheres. And like these objects in our solar system, clouds appear to be abundant in substellar atmospheres. So here on the left, I'm again showing a collection of transmission spectra for 10 hot Jupiters, or highly irradiated Jupiter-like planets, where you can see that many of these spectra show damped absorption features and sloped or flattened optical spectra, all of which is indicative of some optically thick absorber of stellar photons, like clouds. Clouds may also have been observed directly in the atmospheres of brown dwarfs. So brown dwarfs are substellar in mass with radii close to Jupiter. Also, they have effective temperatures similar to many of the planets that we are now observing. And so thus we expect that their atmospheric properties are really similar to a lot of giant planets. But we have better data for them, and in that data, we see broad absorption feature in the infrared that's thought to be caused by silica clouds in their atmospheres. And clouds are also thought to contribute to observed spectral variability. So here on the far right, I'm showing an emission spectra of a brown dwarf, the same brown dwarf, but at 2 different times, where you can see the amplitude of the spectra varies significantly. And this is thought to be due to clouds. Okay. So clouds often dramatically impact observations of substellar objects. And so given this, it's worth understanding clouds from first principles. So I approach the study of clouds using the community aerosol and radiation model for atmospheres known as CARMA. So CARMA is this really powerful code that has been applied to nearly every planetary body in our solar system with an appreciable atmosphere, and has been used to reproduce data all the way from Earth to Pluto, so really high resolution data sets of clouds. So it's this well-tested code, and it works on a Eulerian grid of particle size and altitude, where particles can grow and move into larger bins, as well as evaporate and move to smaller bins. And particles can also be transported vertically along this grid. And so CARMA is a particularly powerful tool because it starts from first principles, and then it calculates the cloud properties that determine what we observe. So namely, it calculates the fully resolved cloud particle size distribution for a variety of cloud species as a function of time. And so this is what a typical CARMA setup looks like here on the right. So here, altitude in the atmosphere Z is on the right, and the temperature, pressure, and pacing as you move to depths is on your left. So we'll have a reservoir of condensable gases in the deep atmosphere that can be mixed upwards over time. Once this gas reaches a region of the atmosphere where it's supersaturated, cloud particles will form via microphysics. Once those cloud particles form, they themselves can be vertically mixed or settle gravitationally.
What's the relevant timescales here for the time independence? Is this like a turbulent kind of shorter timescales, or is this like a longer evolutionary timescale?
Yeah, that's a great question. So what tends to be important in this 1D setup, although as I'll talk about really briefly later, we're also looking at 2D and 3D, is the parameterized vertical mixing. So you really have to see, well, there's a timescales associated with each of the microphysical processes that form clouds, but something that really determines this, so those tend to be short compared to the time it takes to actually get the condensable gases to where they need to be to form clouds. But interestingly, you do see variability in what the clouds look like as a function of time from these interplane timescales. So really long diffusion timescales versus short microphysical timescales. And that variability is really interesting. Lots of different timescales associated with it.
Yeah, so is Karma an open access code that anybody can use?
Karma is open access, not in the version that I use just yet. So I took a version that was suited for Earth. So it's still one of the bases for Earth climate models, though highly parameterized now for water clouds. And so what I did actually here is I really gutted the microphysical background of it and I really thought carefully about all the processes that we're putting in and how we can do this in a way that's really flexible for different cloud species. So my version is not yet open source, although I hope to make it open source. But if anybody wants it, they can have it. But yeah, I do just want to emphasize. So I'll talk a bit more qualitatively about the microphysical processes in just a moment. But before, I just want to emphasize that this is really not a black box. So we've carefully thought about each of the microphysical processes that we're considering. And so we're really not looking at a black box, we're looking at physics.
So this is 2D, right? Or is it 3D?
So in the version for most of this talk I'll be discussing, it's 1D, so just height and particle size. But we do have a now 2D working model, so hopefully more results on this soon. I'll show a teaser for that. And I'd love to make this fully 3D, so just fully coupled with a general circulation model for atmospheres. Ideally with 3D to transfer in there as well. So I could imagine clouds having a really interesting, well, we know that they have a really interesting feedback on atmospheric dynamics. And the microphysics really matters with that.
The faculty at NYU Abu Dhabi, Ian Dixon,
yes.
He has actually 3D models, right? He said the circulation, so they're very rare. They're very also computationally intensive.
He has 3D models, although I should keep up to date. I think the cloud code that he uses is highly, it's not a full microphysical model, it's more parameterized.
Yeah.
There's one group in the UK that has combined the two, microphysics and 3D radiative transfer, but the computation time is 1-to-1 with real time. So you're just seeing the initial conditions.
Wow.
So it's to some extent, it's just a time scale problem, right? Like in 2 years, we can run these models. A fun fact is that Earth cloud simulations, we can do a really great job of predicting the weather for the next day, but it takes 2 days to run. So we're getting there. But I do have some ideas for computationally speeding up the full 3D.
Yeah,
but you have to get rid of some of the feedback.
Like emulators, like technologies. Really would be helpful. Thanks.
Okay, so I want to focus on these 3 key microphysical processes of cloud formation that we consider. And so the first one is nucleation. So this happens when a supersaturated background gas will nucleate onto a seed particle and form a cloud. And there can also be, and I should say that all of these processes depend on your background atmospheric conditions as well as the material properties of the particular cloud particle or cloud species that you're considering. So there can be heterogeneous nucleation where you form on a seed particle. And there can also be homogeneous nucleation where a cloud forms without the presence of a seed. And whether a species nucleates heterogeneously or homogenously or not at all depends primarily on the species surface energy, which comes into the equation here in this exponential term. So a strong function of this parameter. Clouds can then grow via condensation, where a condensable molecule will diffuse along the path until it interacts with the cloud particle and condensational growth will occur. And in our models, this is almost always limited just by the diffusion time, how long it takes you to get your species to the cloud particle. And then clouds can also grow via coagulation, where 2 cloud particles collide and form either a spherical particle or an aggregate. And in our simulations, this is often limited by the number density of the cloud particles that you have. And so here's a primer of some of the results that I calculate with Karma. So here I'm showing particle radius on the x-axis and pressure in the atmosphere on the y-axis. And we're plotting condensed mass density of cloud particles, where each color represents a different cloud species. And so as you can see, each cloud species forms at a different time, at a different height in the atmosphere, and reaches different vertical extents with different particle sizes. And then our results also tend to reach the steady state, as there's some variability, which may very well be real, like the climate cycles that we see on Earth or Venus. And so I'm actually really interested in this variability for several reasons, but for the rest of this talk, I'll be focusing on time average solutions. And so with these results, I can uncover the likely impact that clouds have on atmospheric observables. And I'll again emphasize that quantifying this impact is crucial when we want to determine the properties, the fundamental properties of planetary atmospheres. So we can answer key questions such as the impact of a particle size distribution on the observed spectra. So here in the top plot, I'm showing the, in black, I'm showing a cloud, well, a hot Jupiter transition spectra with our full cloud particle distributions. And then in blue, I'm showing the same transmission spectra for the same hot Jupiter, where we conserve total cloud mass, but have an average cloud particle size for each cloud species. So as you can see, both the amplitude and the shape of the transmission spectra vary significantly, and this is particularly true in the optical and near the broad infrared absorption features that you can see from the clouds in the far right. Okay, so this indicates that understanding the cloud particle size distribution is incredibly important when interpreting observed spectra. And then because our model also considers barriers to cloud formation, we can determine which cloud species dominates the observed spectra. And so here again in black, I'm showing the transmission spectra, this time for a different hot Jupiter.
So if you want to have like a little pointer, like physical pointer too.
I'm probably not going to be great at this. But yeah, in black here, in black here, we have a full cloud particle transmission spectra with all the cloud species that form. And then here in gray, you see the cloud-free transmission spectra. So what the spectra look like without these clouds. So you can already see the huge impact that clouds have on the spectra. And then in the colors here, we're showing what the transmission spectra would look like if you only considered a single cloud species that forms in the model. And so in this case, here in purple, these magnesium silicate clouds dominate the cloud opacity across a broad wavelength range where they also shape the total spectra. Okay. And then in addition to impacting spectra, clouds can also serve as probes of planetary properties, such as their interior thermal structure. So here I'm showing emission opacities as a function of wavelength and pressure in the atmosphere for a planet with the same upper atmosphere thermal structure, but different internal thermal structures. And here the dotted white line shows the location where the clouds become opaque. So for a high entropy planet with a hotter interior, clouds are opaque only up as high as 0.1 bar, so really high in the atmosphere, compared to the planet with a lower entropy, cooler interior, where clouds only become opaque at depth of around 10 bars. So clouds may thus be able to serve as probes of internal thermal properties because they're sensitive to these planetary properties across a range of scales.
When you say interior structure, you just mean gravity?
I mean thermal, like pressure, temperature structure. And this is really relevant for hot Jupiters because they're inflated.
No structure.
Oh, you mean as in like a wind or dynamical structure?
Okay.
Yeah, no. So yeah, the like wind dynamics, all the background is the same. What we've done here is a hotter interior and a cooler interior. And it's important for the question of hot Jupiters because some are inflated, which indicates that they have higher internal heat than you would expect. And then with this framework, we can also predict how clouds will look at different locations on a given planet. And so here I'm again showing cloud particle mass densities as a function of particle radius and pressure. And here for different locations on the same planet, where again, each color represents a different cloud species. And for this case, we're looking at cloud properties on a relatively hot Jupiter. So these planets are often tidally locked, where they have extreme insolation gradients, so a permanent day side and a permanent night side. This gradient and insolation drives a super rotating equatorial jet, which tries to smooth out this gradient, but it does so less efficiently at hotter temperatures where re-radiation dominates. And so at hotter temperatures, where its flow is less efficient at equilibrium temperatures, you'll have a hot day side, a very hot eastern limb, a cool night side, and then a relatively cold western limb. And so I'm really interested in these relatively hot Jupiters because the atmospheric inhomogeneities and their high temperatures mean that we expect different cloud species to form at different locations on the same planet. So they're really exciting cloud laboratories.
But if these are hot Jupiters, they're hardly locked, right? So it's the same side always face, having the sun side, right? So it's not like the night side is always the night side.
Yes. Yes, absolutely. And so, so that should, and in the case where you have irradiation starting to become more efficient, but you still have some jet equilibration, you get really high temperature contrast across the planet. And because we expect the different cloud species to form in this temperature range, we also expect that a cloud should vary really significantly on a given planet. So we can test from observations how good our cloud models work from these planets really nicely. And indeed, we do predict that clouds should look different on different places. So on the hotter eastern limb, few cloud species form. They form relatively high in the atmosphere and they grow to relatively small sizes. While on the cooler western limb, we expect many more cloud species to form. They should grow to relatively larger sizes and they'll form deeper in the atmosphere. And the poles represent an intermediate case between these two. And these cloud properties can translate into transmission spectra that look significantly different in both amplitude and shape on the different areas of the planet. So here again in black, I'm showing the full transmission spectra on the east and western limbs. In gray, I'm showing what the cloud-free transmission spectra would look like on the east limb. And then in blue, I'm showing the opacity continuum due to clouds. So on the west limb, cloud opacity is really significant, where it damps spectral features across a very broad wavelength range. But on the east limb, clouds contribute to this muted and sloped optical spectrum, an intriguing clear window around 3 to 7 microns, which may allow us to peer through the clouds. And then in the farther infrared, we see these crystalline features, these absorption features here due to silicon and aluminum clouds in their atmospheres. And yes, I should say that collaborators and I will probe these broad absorption features in the infrared with James Webb Cycle 1. So I'm really looking forward to that. But what this says,
sorry, this is very naive, but I'm trying to understand where the window comes in. Is that because the different cloud species have different densities of particles that certain wavelengths can't get through, or how?
Yeah, that's a good way to think about it. So it's both the species that you're looking at. So silica clouds are really opaque everywhere, but we're also forming silica clouds here on the east limb. Well, in this case, we must be because we have a silica limb, but they just form to such smaller particle sizes that at some wavelengths where you expect a dip in their opacity just from their optical constants, you can see that much more clearly if you're looking at small particles than large. Large particles will still blur it out across even places. Like you can see, actually not in this case. They'll just totally dominate the opacity. So it's particle size and speed dependent and height in the atmosphere. What this demonstrates is to really understand planetary properties, we'll be greatly benefited by looking at these planets in 3D. So here, the east limb gives us much more information about the planet than the west limb. And indeed, with these mock spectra, I've shown that clouds are likely to enhance observed atmospheric inhomogeneity in a way that should be clearly visible with James Webb. So what I'm showing here is 2 scale limb radii differences in the case of a cloudy atmosphere on the top and a clear atmosphere on the bottom. So in a cloudy atmosphere, the limbs look significantly more inhomogeneous than in the clear case, which still has limb inhomogeneity just due to temperature differences alone. So you can kind of see here this hotter limb has a bit more of a radial difference. But with the cloudy cases, it's far exacerbated. And I've developed a tool for probing this atmospheric inhomogeneity really cheaply using James Webb. So it should only take 2 transits. And so I've also been working on interpreting observations of exoplanets in emission, reflection, and transmission using a new 2-dimensional model where we infect this 1D column around the superrotating equatorial winds of a hot Jupiter. So here I'm again showing condensed cloud mass species as a function, now this time of planetary longitude and pressure in the atmosphere. And so using these models, we can really robustly determine the impact of clouds on things like exoplanet phase curves. These models should become increasingly more useful with the launch of JWST. So this will allow us to uncover atmospheric trends across a range of planets. And so I'm showing one such trend that's already been observed here. So this is for hot Jupiters, where we're looking at brightness temperatures as a function of the planetary equilibrium temperature. Where what we find is that on the day side of these planets, as you increase the equilibrium temperature, so as they're orbiting closer to their host stars, the day side temperatures increase monotonically, but the night side temperatures remain relatively constant across this broad range and equilibrium temperature, even as their day sides heat up. And so we modeled clouds in these atmospheres and found that the constant night side temperatures are really a standard outcome of having the abundant production of spectrally active silicate clouds. And so what we're actually looking at here across this range is the silicate cloud top, which happens to form at around the same temperature. This further demonstrates that clouds shape observations in planetary climate. So what we're looking at in these observations of brightness temperatures are clouds. Okay, so whirlwind of clouds.
Oh, sorry, just a quick question on the last slide. Why did your models cut off at the equilibrium temperature of like 2250?
Yeah, so we cut off here at 2100 Kelvin for both a practical reason and a theoretical reason. The practical reason is that the general circulation models that we had access to ended at 2100 Kelvin, but the reason that they did that is because that's when you start transitioning to things like H- opacity being significant. And also having more like SIO, well, we think absorbers in the atmosphere that really change the regime of the atmosphere that we're looking at. So we think observationally that happens around 2150 Kelvin. Cool. Not that they couldn't be modeled, but
Right, yeah, it's just technically understand.
So I've discussed the importance of understanding clouds and substellar atmospheres, which is crucially important for constraining their properties. But now let's turn our attention to protoplanetary disks. So these are locations of planet formation. And in particular, we'll talk about the interesting question of how much total mass is in these systems. And so the question of how much mass is in protoplanetary disks is fundamental for planet formation and evolution. So the amount of total mass in the system influences the mass, the composition, and the distribution of the planets that form. And so, let's see. So really the total disk mass regulates specific planet formation processes, particularly those where the background gas affects the evolution of the solids. So there's a whole suite of really popular processes now that fit into that criteria. Okay, so we need to nail this down, and we want to figure out the initial conditions of planet formation. And so the most common tracers of protoplanetary disk properties are dust or different trace gas species. However, when we're using dust to trace the total disk mass, we know that there are things that should change the dust to gas ratio from the typically assumed interstellar value. So things like grain growth and drift that alter the dust to gas ratio throughout the disk as a function of time. And there's now, so CO gas is the one that's most commonly used for trace gas to trace the total disk mass. Because it's relatively easy to observe. But now there's a whole suite of observations that suggest that CO is depleted or missing in disks. And so as such, there's reason to question the tracer to H2 ratios that we're using here. And it also begs the questions, how can we measure the total mass without an assumed tracer to H2 ratio? And also what is happening to all the CO? And really getting to the bottom of these questions is crucially important for understanding the fundamental properties of disks and the initial conditions of planet formation. And so I'll get back to CO a little bit later in the talk. I'll start by addressing the question of how much total mass is in these systems. And I began addressing this question by using recent resolved multi-wavelength observations of disks in the millimeter. So here I'm showing observations of the same disk, TW Hydra, at different wavelengths, where you can see that the disk appears significantly smaller in radial scale as we move to longer wavelengths. And to introduce some quick terminology, I refer to the maximum radius in which emission cuts off at a particular wavelength as a dust line. And so, as others have suggested, these observations may be signatures of particle drift. And so I'll take a step back for a moment to talk about the two processes that can limit particle growth in disks. And so here I'm showcasing work done by one of my students, Elizabeth Gunnerman, who just started graduate school at Harvard this fall. Okay. So the process that's the most relevant in the inner disk is fragmentation. And fragmentation can be really significant for a range of particle sizes throughout the disk, or can only be relevant in only a narrow region of the innermost disk, depending on the material properties that you assume. But the likelihood that a grain will fragment, so there I was showing how likely it would fragment based on how aggregate it is, but it depends more on this aggregate, more than the aggregate properties. So here let's consider the composition of the grain, and thus the grain's specific material properties such as the Young modulus and the surface tension, which determine how likely it is to fragment. So just here you can see how silicate particles here in yellow are much more likely to fragment than solid particles in purple. And if we consider that the particle composition changes throughout the disk, we find that there may be a phase space in the disk where neither fragmentation or drift are significant barriers to continued particle growth. So here in the inner disk, depending on your composition, particles will be limited by fragmentation. Then there may be a region of the disk where particles can grow unimpeded, and then a region in the outer disk where particle growth is limited by drift. And so as we're concerned with the dust lines in the outer disk, let's talk about drift in more detail. So particles drift in disks because the gas feels an outward pressure gradient that enforces a drag on the particles, which removes some of their angular momentum and causes them to inspiral towards their host star. And so I'll take just a little bit of time walking through this equation, since it will lead to the key expression for this portion of the talk. Okay, so the drift time scale of a particle is given by its orbital distance divided by this term u naught, which is the velocity difference between the local gas velocity and the Keplerian velocity. And then you have the stopping time parameter tau s, and that's because the particles are neither quite at the gas velocity nor at the Keplerian velocity. And so we observe particles that are relatively small, such that they have stopping times less than 1. And in this regime, larger particles will drift faster. And we can write the stopping time in terms of standard disk parameters and then rewrite the drift time scale. So this time scale is exactly the same as I've put here above, but it depends explicitly on the gas surface density. And you can imagine why it would depend on the gas surface density, because if you have more gas drag, if you have more gas, then you'll have more gas drag if you consider a fixed particle. And that will change the stopping time for a particle of a fixed size. And if we rearrange this equation like this, we see that we can derive the total disk surface density as a function of radius if we know the rest of these quantities. So in particular, if we know the maximum radius in which particles are a given size are present. And so thus, if we have some a priori knowledge of the particle's drift timescale, then we can use this expression to derive the total disk surface density without assuming a tracer to H2 ratio.
I was going to ask, how would you determine T drift? Like what would go into that?
Yes, so that leads to the main assumption of this. So to motivate my choice for the drift timescale, here I'm showing a dust evolution simulation where we're looking at the surface density in dust grains as a function of radius in the disk and particle size. And so here we're plotting different limits to growth, but I really want you to focus on the red dashed line, which is the limit where particles will grow to before they drift inwards rapidly towards their host star. So as you can see in the outer disk at late times, particle drift becomes important and collisional fragmentation is less relevant in stopping particle growth. And so the maximum particle size at a given time, let's see, that's my next one. Okay. The maximum particle size that you'll grow to at a given radius will be the particle size who's grown to the maximum size in that location before drifting inwards. So a particle whose growth time scale is roughly equal to the local drift time scale. And then if you look at a given radius, as a function of time, you can see that this maximum size decreases. So we can therefore expect that the largest particle at a given radius as a function of time will be the particle whose drift time scale is comparable to its growth time scale and comparable to the age of the system. So this is a particle that's had the entire age of the system to grow up to the maximum size that it can, but it's just about to drift inwards. Okay. And oh, we won't use this right now, but I do want to mention that the dust to gas ratio is also decreasing with time. But given this, we're assuming that the drift time scale is comparable to the age of the system.
I think of it even so it's 1 centimeter. So these are what's the composition then? This is, you mentioned particle sizes, but these are like huge things. Right?
Yeah, so they're not quite as centimeter in our disk. Here we're looking at
so not an altitude, but I'm just saying like looking at the max, right? So it's 10, 1 to 10 centimeters.
yeah,
And
and
what are these things? Like like really this, like you would call them like what's the composition?
yeah, it's a good question. So we do think that the composition changes significantly throughout the disk. I think this is something we'll really get a handle on with James Webb, where we can start looking at these features of different ice particles. But there's a standard assumption where you're icy outside of the ice line location where you then become hot and then you become a different ice composition. So people make assumptions like this, and then there's also reason to think that you inherit some compositions from the interstellar medium, but the composition is not well constrained, although I think it will be much better constrained soon. You can also get some constraints from reflected light. And then whether or not they're aggregate and fluffy or compact is also something that we're starting to get a handle on from observation. So it turns out if they're too fluffy, you really wash out a lot of the observations that we see. You don't see a decreasing disk radial extent with wavelength because you then get these fluffy particles that make it look like you would have a certain disk size as a function of wavelength. That's I didn't really give you the background for that statement, but we're starting to get a handle on what their composition and properties are. But we have to make some assumptions that turn out to actually weirdly not be that relevant for this. Okay. So now that we've assumed the drift time scale of particles is roughly the age of the system, we can determine the gas surface density as a function of radius if we know the maximum particle size at a given radius. And so we can determine the particle size if the observed wavelength roughly corresponds to the particle size dominating the observed emission at that wavelength. And we can measure the disk size to determine the radius in which those particles are the maximally sized grains. And doing this, I really want to emphasize, does not depend on a tracer to H2 ratio. And that's because we just care about how fast the particles drift, which depends on their size, and not on how many particles are present. So here on the right is a quick visualization of what this new picture of disks looks like. So here, particles, relatively large particles of size S1, are present throughout the disk until they reach a radius where their timescales are equal, so drift, growth, and the age of the system. And if you were to look at this disk at an observing wavelength comparable to size S1, you would see a disk with this radial extent. And then the same is true if you look at smaller particles of size S2, which are present throughout the disk until they reach a radius where their timescales are equal. And again, for even smaller particles of size S3, where if you were to look at this disk at a shorter observing wavelength comparable to size S3, you would see a much more radially extended system. And so I've applied this model to 7 protoplanetary disks with previous millimeter observations that show decreasing disk radial extent as a function of wavelength. So here I'm showing observations for 3 out of the 7 disks in our sample. And as a technical aside, this is how we're actually measuring the disk outer edge, which is important because it's a fundamental quantity in our modeling. So the maximum radius in which particles of a given size are present.
Wait, should I just understand it as if you go to some lower wavelength and the disk doesn't change, you've hit your maximum? Like you can kind of know.
Yeah, if you go to a lower wavelength and the disk doesn't change, it tells you several things. It could tell you that you're not in a drift-limited regime. So it does take particles some period of time to grow up to a size where you're drifting. So we don't expect this to be true for very, very young disks, depending on something to do with particle growth. And then you could also, so I haven't talked about substructure here, but I could talk about it in more detail, but there's other things that could break this. So that's why we really want to start by looking at disks that do show this strong signature. And so to measure the disk outer edge, we model the disk interferometric visibilities using a Nuclear profile. And so I'll just mention here on the right briefly that our method for finding the true disk outer edge, shown here in blue, finds the true disk outer edge even if there's confounding dips in brightness due to disk substructure. All right, so here I'm showing the total gaseous surface densities for the disks in my sample. So here the black points are the surface densities derived from dust lines, and the red and blue lines are previously derived surface density profiles from either CO observations or combined multi-wavelength observations of dust. And what I've done here is normalize these profiles so as to match the surface densities derived from dust lines. And you can imagine if we had many more points from dust lines, we could just directly fit the profile shapes. And so that's what I've done here on the bottom right for the disk around layer 25, where the dashed black line is the fit just from our surface density points. But because we have so few points right now, it's encouraging that the previously derived profiles match the shape of the dust line derived points quite well. And this really did not have to be the case. And so actually for different disks, you have different slopes, and for all of them, the dust line derived points match the profiles quite well. So TLU hydroid, FT tau, different profile shapes, but the dust line points are still matched by these previously determined profiles, renormalized profiles. And so all of this is what makes us think that this model might be doing well, or first indication. And so we can now place these dust line derived masses in context. So here on the left, in black, I'm showing the surface densities derived from dust lines for 2 disks in our sample. And I'm comparing those to previous estimates from other tracers like dust or CO, and the minimum mass solar nebula, so the minimum mass needed to form our solar system. And so the disks in our sample are 9 to 27% of their host stellar mass. So this is significantly more massive than the minimum mass solar nebula, which is around 2% of the sun's mass. The disks are also 2 to 15 times more massive than estimates from integrated optically bent dust emission, assuming an interstellar medium dust to gas ratio. And for the 3 disks in our sample with CO emission, our estimates are 30, 40, and 115 times more massive than estimates for CO, indicating that dust may be a more robust tracer of total mass than CO, as we uncover this reduced dust to gas ratio that's roughly constant across our sample, while the CO to H2 ratio varies more strongly, which I'll come back to later in this talk. And so now here I'm plotting the tumor Q stability parameter as a function of radius for the disks in our sample. So tumor Q parameter less than about 1 is where you expect to be gravitationally collapsing under your own self-gravity. And so all of the disks in my sample are stable to gravitational collapse, except for 1 disk which approaches this limit. And actually at the radii where it approaches the instability limit, we do see some features in its high resolution imaging that may support gravitational instability. But note that all of the disks in our sample have low Q values at certain radii. And so we think that when we form disks, they're marginally unstable. This marginal instability might be helping raise spiral arms that throw material onto the star efficiently. And we really still think all of that is happening. But at late times, you really need something like magnetorotational instability or disk winds to kick in to drive further accretion. And it's still a big mystery how disks are able to accrete efficiently at late times. But maybe if some of the disks, at least the bright massive disks in our sample, maintain much of their mass at late times, you don't actually need a lot of these processes to be happening. At least as some of these disks seem to maintain much of their mass. And in our modeling thus far, it has not been required to know an expected dust surface density. But given our results, we can use models of coagulation to compute the dust surface densities, since we know that the maximally sized particle at a given location has a growth time scale that's also roughly equal to the age of the system. And so here I'm showing surface densities for disk around FT tau, where the total dust line derived surface density is shown in blue, so the total mass, and then the observed dust surface density is in solid black. And here the dashed lines are an analytic and numerical treatment of particle coagulation. That's given us modeled dust surface densities. And so for the disks in our sample, we derived depleted dust to gas ratios of around 10 to the minus 3, which is really a common outcome of many models of grain growth and drift. And so in our models, the extra gas, so the order of magnitude of dust that we've lost, has drifted inwards to the inner disk. But you can also paint an inconsistent picture here with some of that drifting dust being incorporated into planets over time. And it's worth noting that the dust mass in these models, so the disk's dust mass, was an order of magnitude larger at early times. And also being able to constrain both the dust and gaseous surface densities using this method gives us an avenue to empirically constrain the dust opacity, which is important because that's one of the largest sources of uncertainties and investigations of protoplanetary disks.
So what about irradiation by the star, right? These are young stars that still like X-ray active.
Mm-hmm.
So is that included in there too, or do you only care about the midplane where it kind of should be more shielded?
So what we really care about here, where the flares will come into play, is likely in how much mixing you have. So the one thing that comes into the models of coagulation that doesn't come into the models of drift is how much turbulent lofting you have, which drives the coagulation. So you can imagine if something like an outburst of irradiation drives further mixing in the disk, that could change this picture. Although if it's just an outburst, I expect that would be within the uncertainties, the large unquantified uncertainties in this model. Okay, so we can learn a lot using this model that I haven't talked about here. So all the way from the aggregate nature of the dust grains, which I mentioned briefly, to the nature of the disk morphological features. Overall, here's this new picture of disks, where they're order of magnitude more massive than previously appreciated. So they may be significantly more massive. So the total gas mass, well, the total dust mass is the same, but the total gas mass is larger. And these qualitative changes to models of protoplanetary disks have significant implications for planet formation processes, particularly for those processes where the total amount of gas affects the evolution of solids. So that will be affected by this picture. And also it's worth noting that because we expect that the disks form with an order of magnitude more dust than we presently observe, this can help bring resolution between tension between observed mass of exoplanet systems and the observed mass of disk dust mass. So it seems like there's much less mass and dust than there should be to form the planets that we see. But if there's an order of magnitude more at early times, then that helps with that tension. All right, so we've discussed the total mass in disks. How much time do I have left?
6 minutes.
6 minutes. I think I can do this for 6 minutes. Okay, but really what is happening to all the CO gas in these systems? And we really want to know the answer to this question because CO has been used as a tracer of nearly every protoplanetary disk property. And so that's affected if there's less CO relative to H2 than we expect. Also, CO is a primary carrier of carbon, so it's key in planetary inheritances. And so to answer this question, I'll be combining the two methods that I've used so far in this talk, so modeling clouds and modeling disks. I'll start by saying that it's not just my modeling that indicates that CO is depleted in disks. So here on the left, I'm showing observations of the disk TLB Hydra. So I'll just do two examples, but there's several in the literature. So here's the disk TLB Hydra, where we're looking at the CO abundance as a function of radius compared to the abundance that you'd expect from observations of the interstellar medium. So CO appears to be significantly depleted across the range of this disk. And we also see similar trends if we look at large samples of disks. So here I'm showing a survey of disks in Lupus, where the dust mass of the disks, so here they're ordered by dust mass, spans several orders of magnitude, but the gas mass estimated from CO is roughly constant. So in short, we observe much less CO in disks than would be predicted or than we would expect using previous disk models. And to address this question, I've coupled my model for protoplanetary disks to an adapted version of the model that uses acidic clouds and exoplanet atmospheres. And in this context, I'm modeling the formation of ice on dust and disks. And what turns out to be important in this modeling is that the nucleation and growth processes in this scheme include the Kelvin effect. So the Kelvin effect quantifies the stability of small particles by looking at the surface bonds. Well, so I really like to think about this in terms of geometry, where a small molecule on the surface of a small grain won't be able to molecularly bond to many neighbors as a condensable molecule on the surface of a large grain. So ice forming on large grains is more stable. And the Kelvin effect really causes ice to nucleate and grow more quickly on large particles. And the particle sizes are important here because they actually regulate the level of depletion of gaseous CO. So if we approximate the disk temperature structure like we have here, where the disk is roughly, so here it's vertical, where the disk is roughly isothermal until you reach a layer where surface layer heating is efficient and the disk temperature increases. Then if you're outside of the midplane, you'll expect that there's a region of the disk that's cold enough where ice can form, and then a region that's warm enough where evaporation or photodesorption of the ice particles can occur. And so if an ice particle that forms in the midplane is small, then it can be wafted to the upper regions of the disk where it will release its volatile mantle and less CO gas will be depleted. However, if an ice particle that forms is large, it's not readily lofted. It can maintain its volatile mantle and then cause the gas and continually deplete the gaseous CO. So that's actually what we're showing here on the right. So here we have this initial abundance of CO shown in solid black, which is depleted as in gray when you're forming ice in the midplane. So this gray line here. And then if you were to not incorporate anything about radial diffusion and you let this run out with time, you would eventually have a profile that's set by the midplane saturation vapor pressure. So it will be vertical diffusion will get rid of this concentration gradient of CO. So gas will be continually funneled down to the ice formation region and will be locked up on large particles. And so this is the so-called cold finger effect that can ultimately lead to a large depletion of gaseous CO. But the particles and gas in the system evolve radially as well as vertically. So at early times, gas will be depleted the fastest just exterior to the midplane CO ice line, where the vertical diffusion timescales are short. Then as time goes on, the depletion will become larger in the outer disk, which has a larger maximum depletion amount, but has a higher diffusion timescale because the disk layers at larger radii. And then in the inner disk, ice particles will drift inwards and release their volatile content. And this can lead there to be an enhanced abundance of CO gas in the inner disk interior to the midplane CO ice line that can then be accreted onto the star. And so let me quickly walk you through the evolution of CO in disks. So CO gas is continually mixed down towards the midplane, where it forms ice on large particles. These large particles will eventually drift inwards toward their host star until they reach a region where they'll release their volatile CO. The CO can then enhance, well, actually, there's some interesting cycling that occurs around the midplane. That's worth noting. But then in the inner disk, where there's this enhanced abundance of CO relative to H2, it will be accreted to the host, onto the host star more efficiently with time.
It's accreted onto the star?
Yes, well, just accretion, just if you assume that it follows a gas accretion rate onto the host star, but with an enhanced CO to H2 abundance than you would expect, because you're really shuttling all of your gaseous CO into the inner disk. And so when we model observed disks, we find good agreement here between our results and observations, as we're showing these small plots B through E here. And in our modeling, we find that this depends strongly on diffusion. So once you've assumed that, or once you've modeled that the ice forms on large particles, the amount of depletion in your disk is controlled by the amount of diffusion that has happened on the lifetime of the disk. And so that's what we're showing here. And I'll note that this process is also applicable to other volatiles in disks. So really the microphysical processes of ice formation regulates observed CO abundances and also determines the radial compositions of protoplanetary disks. In using this model, I'm able to constrain both the solid and gaseous CO inventory at the disk midplane where planets form, and constrain the bulk disk diffusivities, and resolve tension and estimates of disk mass using different observational tracers. So these are three crucial parameters that determine planetary formation. Okay. All right, so I've talked about understanding substellar atmospheres and disks, and I'm definitely out of time, so I'll leave you with my conclusions. Thank you so much.
Any questions? Let's see, Richard.
Yeah, thanks for the nice talk. I'm wondering about how dust grains grow in terms of their geometry. Is it always spherical, or are there ellipticities that could occur, and what would be the cause of them?
Did you say vorticity?
Well, no, ellipticity, like if it were to grow in a non-spherical way, for instance.
Yeah, good question. So I don't think we have a great answer, but the ways that we typically think about it is that you might form as an aggregate, at least at small sizes. So you have these initial monomers inherited from the interstellar medium, form some aggregate. But you have to remember that these particles are interacting with their mass and gas on an orbital time. Basically, you're getting to interact with a lot of mass. And so we think that they are compactified fairly quickly. So you form some kind of compact grain with some amount of aggregate nature maybe left. In terms of elliptical versus spherical, I haven't thought about that question as much in particular, although I think it's interesting. I could imagine I mean, now I'm thinking about like a Muamua type scenario, so I would just be spitballing to talk about it, but it doesn't sound like obviously something that couldn't happen. But it's not something that's given much thought to, ellipticity in particular.
Yeah, it'll be interesting to see if it affects the results. Thanks.
Oh, well, I will say, so for disk, you might expect this to have, like, so for whether something's aggregate or compact, you might expect that to be really significant in our determination of the disk mass. But what we found is that if you're looking at an aggregate in the regime where you know the monomer size, it often the filling factor and the density cancels out the what you're looking at optically, such that it doesn't really matter if it's fluffy or compact. It doesn't matter as much for drift. Well, because basically you're observing an apparent size that corresponds to the density. Actually, maybe I have a plot here. But yeah, in terms of elliptical nature of the aggregate, that'd be interesting. Although I think we get a similar lack of dependence. Oh yeah, so even if they're aggregates, if you believe the optical properties that we expect for aggregates, the observed size relates the actual size as by the filling factor, so how fluffy it is. So if you divide the observed size by the filling factor, but you also do the same thing for the density. So these filling factors cancel and you end up with the same expression for disk surface density that we had before. It does change growth more. So it does change the dust surface density that you expect, but it doesn't change the total gaseous surface density.
Yeah, but maybe a long ellipse that might have some filling factor would behave different than a sphere that has a same filling factor.
That's interesting. It might have some weird tumbling motion. Good question.
Any other question online or in the audience? I don't see anything here. All right. Let's thank Diana again. Thanks, everyone. See you next time.